If you look at this diagram, you see a basic recipe. The concept of tea transforms downward into its raw ingredients: water, milk, and sugar. In computer science, a grammar works exactly the same way. We start with a high-level concept and substitute it step by step into its individual parts. This formal process of substitution is called derivation. As we switch to actual grammar rules on screen, you can see our starting symbols on the left mapping to specific replacements on the right. We follow these rules, swapping pieces out until there are no substitutable ingredients left. Let's apply this. We begin with our start symbol, S. Using our first rule, we substitute that S, transforming it directly into the intermediate form, lowercase a, uppercase a. We still have an uppercase letter, a non-terminal, so the derivation must continue. We substitute that uppercase a with a lowercase b. Now we have AB. Because this final string consists entirely of terminal characters, the derivation process stops. Derivation acts as the mechanical engine of a grammar. It systematically converts abstract, high-level non-terminals into tangible, valid strings of code that a computer can actually process. Take a look at this animated derivation. When a grammar rule points back to itself, it creates a recursive loop. As this loop continues running, a single concise rule can generate an infinite variety of distinct strings, cascading outward. When we group that entire mathematical set of generated strings together, we define it as the language of that specific grammar. Let's examine the terminology of the derivation steps. Any string that appears during this process is classified as a sentential form. As shown by the grouping bracket, even a mix of terminals and non-terminals counts. Think of these as the work in progress. A sentence, on the other hand, is strictly the finished product. It is only the final string at the end of the derivation that contains 0 non-terminals. A classic point of failure in compiler analysis is mixing up these two terms. Every sentence is a sentential form, but not every sentential form is a sentence. Parsers demand absolute precision, so you must keep the work in progress separate from the final product. Notice the contrast in the split screen. While derivation flows downward to generate code, a compiler's parser works in the exact opposite direction. It takes the finished sentence, like ID plus ID, and reverse engineers the derivation upward, collapsing it all the way back to the start symbol. When we expand a start symbol and get a sentential form with multiple non-terminals simultaneously, we face a branching choice. Look at the pulsing A and B. Which one do we expand first? To resolve this, we use strict algorithmic rules. Leftmost derivation means exactly what it sounds like. At every single step, you target the leftmost non-terminal for expansion. Applying this to our string, the indicator isolates the A first, expanding it to AA. We check again. The leftmost non-terminal is still A, so we expand it into a lowercase a. Now, the only non-terminal left is B, which we substitute to reach the target string, AAB. Let's test the inverse logic. Pause the video here and try to generate that exact same string, but this time strictly target the rightmost non-terminal. Here is the correct path. Starting with AB, your rightmost non-terminal is B, so it expands to a lowercase b first. Next, you move left to the A, expand it to AA, and finally expand that remaining A to reach the same result, AAB. Notice that both methods produce the identical final sentence, but the structural path taken to get there dictates the architectural design of the compiler reading the code. These structural paths map to real-world systems. Top-down parsers are built explicitly to execute leftmost derivations. Conversely, bottom-up parsers are designed to execute the exact reverse of rightmost derivations. This table summarizes the core framework of the unit. You have your sentence, containing only terminals, your sentential forms representing intermediate steps, top-down parsing linked to LMD, and bottom-up parsing linked to reverse RMD. But there is a glaring limitation. Tracking complex substitutions using purely linear text quickly becomes difficult to manage. To understand how a compiler structures code, we pull these flat derivations apart and transform them into multidimensional blueprints. Next, we build parse trees.